illustration of it. That's the only thing I've ever ignored previous literature.
That's the biggest.
Chris Hill! All right, so it's my pleasure to introduce Mark Wagner at the end of getting the last word.
All right.
Not quite.
First of all, I do want to thank Gary and Alexander and Declan for arranging this wonderful conference and for doing just a great job of organizing it. And thank you for including me. I appreciate it. Secondly, I do want to say, as the last person, I really do kind of feel like I've been scooped. And that I went through and I kind of made a checklist, and virtually everything I have to say has already been said before. So it does make life a little difficult, but we will go on. I want to start by doing something that I personally consider a little dangerous, because the audience is largely composed of very talented philosophers, and I'm going to lay out what I consider some of my fundamental assumptions right up front. We'll see what happens with that. First of all, I think what we want to do with this whole project is to try to describe our conscious experience of space. That's what we mean by visual space. That's what we want to do. We've shown in various places throughout this weekend that visual space can differ dramatically from physical space under very ordinary circumstances. The only way, though, that we can get to visual space is by having people make judgments or use subjective measures. Since we can't directly observe consciousness, visual space must be operationally defined in terms of the judgments that observers generate. It seems like you have no other choice, since you can't directly record conscious experience. Different measures and varying experimental conditions can lead to different conclusions about the structure of visual space. These two things together leads to the following question, and that is there one unitary visual space, or are there in fact many geometries or many spaces? I think that if you take, oops, I'm using the wrong button. I think if you take these two together, it leads to the conclusion that there are actually many visual spaces. Because once again, if we're accepting the judgments as being what defines our space, and our judgments lead to different outcomes, I think we have to conclude that visual space is a multiplicity instead of one. Now, this conclusion could be wrong in one of three ways. One thing that could be wrong is that, in fact, some judgments don't reflect conscious experience. The second way it could be wrong is that it could be that there really is no inconsistency among the data that we have generated. And then the third possibility is that I'm wrong saying that these two together leads to the conclusion that there's multiple geometries to visual space. Personally, I'm comfortable with the conclusion that those two together implies that there are multiple visual spaces. I think that my talk today and what we've heard from Jim and from Jan and from many others here really kind of, I think, says that this one has to be correct. So the one that I think that is going to be the one I think you should think about the most is this other one. Is it the case that some of our judgments simply don't reflect conscious experience? If you want to hold a unitary vision of visual space, you have to assume that anything inconsistent with that unitary vision of visual space really doesn't reflect your conscious experience. And I leave that as a question for you to think about. You're probably better at resolving that than I am. When I talk to some of my relatives about doing this type of work, the first thing they always ask me is, who cares? Or they make the kind of the basic feeling like, this is all very interesting, but it really doesn't matter. But in truth, it does matter. You know, it really does. You can see that human spatial abilities actually affect performance in all sorts of tasks that people do in the real world, including things like driving, flying, operating trains, sports performance. All these things influence. Largely, by the way, I think that the common bond is anything that makes you go fast is a place where you're going to have problems, or anything that makes it where you have to be really precise. By the way, the last one is not a mistake. I ran across this wonderful court case from 1907 where the whole case turned on whether a person's spatial abilities were good or not. Never, it doesn't matter. There actually are a whole kind of paradigm, whole communities of scientists that approach the problem of visual space in different ways. There are some people use what I call the direct estimation approach. Other people look at size constancy. Other people look at a more multidimensional approach. And I don't think that's exhaustive. I think there are many different approaches that people can take to the problem. In effect, what we have are different paradigms that people follow to look at human spatial perception. I like to start with what I call the direct estimation research. Here you ask observers to generate numbers to estimate size, distance, area, and volume. There's lots of ways to do this. You can use magnitude estimation, you can use category estimation, you can use various production techniques, but there's a whole literature that goes way back that does this. In this literature, they tended to have found that the estimates follow a power function, which has this form. Here, J is the judgment that people give. S is the physical magnitude that people are judging. Lambda is simply a scaling factor, although there are many interpretations. There was one article that had 12 interpretations of this. And then most of the research focuses upon the exponent in this literature. So what does the power function exponent tell you? Well, this is not the best figure in the world, I have to admit, but I had another one that I found that it completely disappeared when I put it on a screen. So this is better than that. But basically, if the exponent is close to 1, then that means that people's judgments are going up in lockstep with the physical quantity that's being judged. If the exponent's greater than 1, then people have kind of a hypersensitivity to large magnitudes. They kind of like they expand too much, as it were, the difference between a moderate size and a big stimulus. On the other hand, most of the time we see things that are less than 1. And when you have an exponent less than 1, that means that you're really not very as sensitive to the difference between a moderate and a large stimulus. So in some ways, people can use this as a measure of your perceptual sensitivity. So far, so good? So I did a meta-analysis of this literature. And to do the meta-analysis, I got 108 articles. And in here, there were like 560 exponents that people generated. I then recorded 40 variables that were related to each exponent, including things like goodness of fit, the experimental conditions under which it was done. And I also derived some variables by combining some of those variables into higher, I guess you might call it higher order variables if we're talking Gibsonian language. This ends up with 22,000 cells. What really drives you nuts, though, is missing data. Because you know what the problem is with missing data? It's easier to find something than it is to be sure that something isn't there. I don't know why I'm laughing. I guess because I'm tired. I'm just going to go on. And so what do you find? Well, overall, what we find is that people are pretty good at judging size and distance. And by the way, the difference between, in my mind, between size and distance, and it's really not a good difference, is distance is largely egocentric. It's from you to the object, whereas size tends to be between two different points out in space, how far apart they are. But people are pretty good at that. I mean, overall, the exponent that we get is 0.96, which is really close to that ideal of 1. Notice I have up there an r squared value. And what r squared is it's how well the judgments that people give correspond to a power function. And you know, there's not many things in psychology that have r squareds like that. So that's pretty impressive. People are not as good at area. There's some tendency for them to be a little less good at judging moderate areas compared to large areas. And the fits, though, to the power function are just as good as long as you're looking at perceptually present areas. You can go down a little bit, though, if you ask people to rely on memory. And so that's one end of the, yeah, I'm not using this right at all. So this would be if you allow for cognitive maps, memory. This is the type of fit you get if you allow just for perceptual types of research. Volume's even worse. People are just not as good at judging volume as they are judging the other dimensions that I have here. But the r squared, the fit to a power function, is still pretty darn good. There are factors that influence how good you are at doing these things. Oops, I keep wanting to do this. Perception generally leads to larger exponents closer to 1 than memory or inference conditions, where inference means where you learn something over time and never actually see it all together as one thing at a time, something like a cognitive map. When people do their research in a lab, they tend to lead to larger power functions, larger exponents, than if they do it in the outside. This one doesn't make sense to me, but it's true. If you don't use a standard, you get higher exponents than if you do use a standard. If you have a small stimulus range, you get larger exponents than you have a large stimulus range. This, by the way, is I guess the legacy of a person named Robert Texanian, some of you may know, and he had a dynamic range theory that just shined throughout the data that I got, because he would predict that. There are other things. These are factors that we'll get back to. You generally get higher exponents under objective instructions, where you ask people to judge the actual physical size of a stimulus. And you get lower exponents if you tell people to just say how it looks. If the stimulus is frontal, like this relative to you, people generally do better, have higher exponents, than if its stimulus is flat, receding in depth. Full Q conditions, where you have plenty of Q's to depth, lead to higher exponents than reduced Q conditions. And old people like us generally have higher exponents than the children. This one I show you just for fun. When you collect 40 variables, you get a lot of significant results. And you get a lot of collinearity in the variables. So I did what any psychologist would do. You know, I go and I do a multiple regression analysis where I try to find the largest set I can of variables that all significantly contribute unique variance to the prediction of the exponent. And then based upon that, I'm able to stick it in here and come up with what you might call general psychophysical equations. It's not as great as you might think, because actually there's more than one solution that works pretty well. I do have a theory for why we saw the data that we saw earlier on, and that is, and it's related to to what Jim was talking about earlier, that Weber's law, in some sense, rules all of psychophysics. And those conditions that lead to more precise judgments are also the conditions that lead to higher exponents. Simple calculus can show that that conditions that produce precise judgments or smaller Weber fractions should produce higher exponents. So the data that we have kind of fits with this. There's a second literature out there that people use to study space perception. And that was one that we've actually had kind of more connection to, I think, over these days. And that is the size constancy research. Typically, these experiments have kind of a standard format. There's an adjustable comparison stimulus that's usually near the observer. Occasionally you find somebody who puts the comparison far away from the observer, but that's super rare. It doesn't happen very much. Then there are standards of a constant size that are placed at various distance from the observer. The observer is asked to adjust the comparison to match each standard. By the way, this is one of the problems with going last. You all know all this, from before. And the observers are accurate for near standards, the ones that are close to where the comparison is, but they can become increasingly inaccurate as the standard grows more distant. There are three possible outcomes. One is constancy. The comparison accurately matches the standard at all distances. Then there's underconstancy, where the comparison is made too small for distance standards, which we interpret as the standard seeming to shrink in size perceptually as you go farther from the person. When I look at this picture I have here, oops, I keep doing that. When I look at this picture I have here, I see what I would consider underconstancy. This card that is nearer to us seems a lot bigger than the car that's back here, but I'm pretty sure that physically they're not all that different from each other. We also have another possibility, which is overconstancy, which is the comparison is made too large for distance standards. That is, the standard seems to grow as distance increases. So I did a meta-analysis of this too. Basically, the review started, I've heard the names mentioned a number of times. Basically this started back in the days where I always say thowless. How do you pronounce it?
I've always said shoeless. I've always said clueless.
Clueless? Yeah, I mean, everything you want to know about space perception, really, you can probably, basically look at Thulus or Thowless. I'll say Thowless because that's what I think of it. He already anticipated pretty much everything I'm going to say here. Also, Brunswick was doing work during this kind of period of time. Based upon this review, there were 125 experimental conditions that I found, and that the judgments were influenced by 4 factors. One factor is instructions, which is, I think, the meaning given to size. Another one is cue conditions, whether there's lots of cues to depth or not very many. Stimulus orientation, whether the stimulus is presented to you frontally or receding away in depth. And then the age of the observers. The general take-home point, before we actually look at that, is that underconstancy results when depth information is unavailable or ignored. So that'll be the rule. And so here's what we found. Instructions influence whether a person generates underconstancy or overconstancy. There were a couple of studies that used what were called perspective instructions by a guy named Carlson. And basically what perspective instructions do is they explicitly train people on the laws of perspective and then invite them to adjust for that. And under these circumstances, people are wildly overconstant. The most distant stimulus is seen as being about 56% larger than the nearest stimulus. Then there are objective instructions where people are asked to judge the actual physical size of the stimulus. And overall, most studies from the period I looked at show overconstancy there too. In this case, less than perspective instructions, but still pretty high. All of this should make Carl very happy because what people use this to argue for, particularly those perspective instructions, is that what people are doing when they produce overconstancy is they're compensating for the fact that, you know, where they're trying to look at the stimulus and then trying to produce the actual veridical physical size of the stimulus when they overcompensate for it. If you have apparent instructions, they're, interestingly enough, here what you're doing is you're saying to people, tell me what it looks like. And if you ask people to say what it looks like, oddly enough, that's what leads most to constancy. I do have a subjective sense, however, that since I did this meta-analysis, the more recent research that's come out with apparent instructions have had kind of a more of a tendency towards going towards underconstancy. I could be wrong about that, but so maybe if for instance, you do a more recent meta-analysis, you might even find a stronger tendency towards underconstancy. Projective instructions ask people to take on an artist's eye view. And in this case, where you ask people to say how much of the visual field something takes up, then people tend to produce very strong underconstancy. The orientation of the stimulus, oh, wait a second, I'm not done yet. That's all for frontally oriented stimuli. If you have people make judgments about stimuli that are oriented in depth, lying flat along the ground, under those circumstances, they pretty much always produce underconstancy. And if you give them projective instructions, it's a super big effect. There are other factors affecting size constancy. Reduced Q conditions, where you don't give sufficient information about depth Qs, tends to lead to very strong underconstancy. There was one study that I feel needs to be replicated that seemed to indicate that if you give people alcohol, they produce underconstancy in their judgments. I don't know what to make out of that, but I just love it so much I have to put it up there. Somebody has to do that again. And then age affects whether people, whether the participants produce underconstancy or overconstancy. And it's just totally in keeping with what Carl said to us before. Very young children tend to have a strong tendency towards underconstancy. As they get older, they move more towards constancy. And then as they get to be adults, there we see a tendency towards overconstancy at that point. Now, I have a model for this, and I have to say it's not at the level of sophistication of what I've heard from Jim and Jan, and it's not. But I have a model to explain this called the transformation theory of size judgment. This is something I have to tell you that Jack Baird and I created together. I know some of you remember Jack Baird. He was a good friend and mentor for me who regrettably passed away lately. Not too long ago. But in any case, we came up with this basic idea that answers one of the first questions that was on the list of things that we were supposed to consider for this conference. And that is, how do you go from the retinal image back to the perceptions that we have of space? Well, here's the diagram I have for this situation. H is the observer's eye height. And then D is how far away the stimulus is in this typical size constancy experiment. S is the actual size of the stimulus. Phi, or you could say phi. I've never heard anybody say fo or fum. But in any case, phi is the orientation of the stimulus. If it's 0, it's flat along the ground. If it's 90 degrees, it's straight up and down. And the process of converting that into the visual angle that hits the eye follows an equation like this. The only reason it's this complex, because as most of you probably know, this is just a variation on the size, distance, and variance hypothesis. But this is one that tries to allow for various orientations all in one formula. But in any case, that's a physical process. I feel like that would take place without error, because it's just a physical process of converting the stimulus into a visual angle. In order to recover physical size, you'd need to do an inverse transformation. And I'm just assuming, I'm just using regular Euclidean geometry to come up with this model. But you'd have to do the following inverse transformation in order to recover the physical size of the stimulus perceptually. But Jack and I basically felt that this is a psychological process. And because it's a psychological process, this is where error can enter in. There's really kind of two places, although there's more if you really think about it, but there's really two places where error can enter in. One is in the distance judgment we have, how far away we think the stimulus is. And based upon the previous meta-analysis that I reported, one would presume that that should follow a power function. And so we put that into the model. We also separately had a model in which we said maybe we're not really fully taking into account the orientation of the stimulus. Maybe instead of really knowing that it's a flat stimulus or really fully take into account that it's a frontally oriented stimulus, that we don't fully take it into account. And then more recently, I kind of generalized this. It's a trivial generalization, but I allowed for both of these two things to vary at one time. This transformation theory of size judgment, I then fit to a whole bunch of data, the data I could find. The early data from about 1920 to 1941 really wasn't set up to do this, because there they reported their data in terms of Brunswick ratios, or here's the one where I'm going to say it wrong, Thouless ratios. So they reported it differently. But then about 1941, Hallway and Boring presented the data in a new way that was more parametric and allowed for the possibility of fitting the data. And so I fit the data to 31 different sets of data that I could find over the years, and basically fit the data pretty well. Here's an example from Epstein in 1963, where we look at the effects of instructions, and it fits with what I was just telling you earlier. This top one is perspective instructions. The next one is objective instructions. Then we have apparent instructions, and there we have projective instructions. Similarly, Baird and Biersdorf. Yes, please.
What is S star divided by S?
Let me see where I'm at. Oh, yes. Basically, what this is the perceived size, which is the size that the person adjusts the comparison, and then S is the actual physical size. And where it's 1, that means that they're adjusting it correctly. If it's more than 1, thanks for asking that question, by the way. If it's more than 1, then that means that we're doing over constancy, we're adjusting it too large. And if it's less than 1, then that means that it's under constancy and we're adjusting it to be too small. Does that make sense? In any case,
Green is the distance in meters?
yeah, I think it is. No. Yeah, it might be inches. I have to tell you, I can't remember. So I'm sorry to say. It's a good point, but I can't remember. It couldn't be feet, because that would be a long ways away. That'd be almost a mile. So it probably is still in inches.
Right.
Yes.
1-5. 15 minutes.
Oh my God. I better go quickly. Yes.
Sorry, I've got to leave in a second. I just wanted to ask you a question. When you were doing your meta-analysis of children's size constancy, were there a range of stimuli such that, say, in the distant stimulus might be quite tall,
Yeah.
as well as the smaller ones that Carl was
Yes,
talking
I
about?
mean, this is combining a lot of data, and so therefore there would be variation in how big the standards were that people used, or how far the most distant one was away. And so, yes, you're absolutely right. I'm averaging across different experimental, arrangements, and so some of that is kind of like, I guess, sort of washed over.
So some of them might be over your head.
Yeah, conceivably.
Okay, thanks.
Yeah,
Not in the child research.
but probably not. Yeah, I mean,
They're mostly small
yeah.
and closer.
There's the answer to your
What
question.
did you say?
Some of the adult studies use really big stimuli that are really far away, but the child studies mostly haven't. They use smaller objects that tend to be fairly close. They got to 4, 5, 10 meters mostly.
Should I go on?
Yes, sorry.
In any case, I think I'll move a little quicker now because I'm finding that more time passed than I thought. But in any case, here are the factors.
For that?
What's that?
Do you have the exponent for that?
I do have those exponents around. Yeah, that's true. Yeah, but in any case, here's the interesting thing to me. In the model, if you look at the exponent, objective instructions lead to a higher exponent in the model than either apparent or projective instructions. Frontal orientation of the stimulus leads to higher exponents than flat. Full Q leads to higher ones than reduced Q, old more than young, which of course is exactly the same pattern that we saw in the data that we looked at earlier in the direct estimation literature. So it seems like there might be a link between the direct estimation literature and the size constancy literature. It's also the case that the applied orientation, or phi, in the model tend to be less than vertical for frontal stimuli and greater than horizontal for flat stimuli. This implies that observers may not fully compensate for the orientation when making a, yes, underneath there it says judgment. I'm going to go forward. There's also multidimensional research that's out there. Both of the two literatures I talked about before are unidimensional types of judgments. Whereas there are some studies that try to get around this limitation by looking at in-depth and frontal stimuli at the same time. I only got like 10 minutes left.
You have 13.
Okay, because I think my intention was to describe my old research, but then I kind of think that just in the interest of time, sounds like most people know the types of things we did. I pounded stakes into random locations in the field, had them judge distance between stakes using 3 methods, had observers judge angles formed by 3 stakes versus using 4 methods. And for all observers, we got the same factor that influenced people's judgments, and that was the orientation of the stimulus relative to the observer. In my quick little move through my results, you can see here's 2 examples of the data I got for distance judgments as a function of the orientation of the stimulus. One is like the smallest amount of variation that I had among my subjects. The other one is the largest. And what we find, and people have said it many times here before, is that that for frontally oriented stimuli, 0 and 180 degrees, the judgments tend to be bigger than for those that are in-depth oriented, which in my figure is 90 degrees. It's also possible to look at the angle judgments that people produce too, in the same sort of way. And the basic finding is that if the angle's looked at across the two legs, it tends to shrink in size. If it's either facing toward you or away from you, it perceptually expands in size. I'm moving on. I wasted too much time in the early part of this. You had people like make little maps of the stimuli out in the field. And what you find is if the squares here are the physical layout of the stimuli, whereas the diamonds are the way that the subjects place them on the map. And as you see, once again, we have a real squishing in the in-depth dimension. I used an affine transformation to describe this, although I want to be careful here because I'm not sure it's what you would call an affine transformation. I'm not sure. But basically, this model says that the C is what I call a compression parameter. And what it does is it says that if C is 0.5, then that means then an in-depth oriented stimulus is seen to be half as big as one that's frontally presented. And I only think of this as a descriptive model. I don't actually, I'm willing to abandon it quickly, as Gary was able to find out, because I see it as being descriptive, but it gives me a kind of a factor that we could look at that describes that compression of the in-depth dimension as compared to the frontal dimension. I also was able to fit it to this same model to the angle data by using a formula I got from Riemannian geometry. And what we found was that pretty much it seemed to fit a Euclidean metric because because the R in that equation reduced it to in all cases. On the other hand, that compression averaged about 0.5, indicating the same physical stimulus seems half as large when oriented in depth as compared to frontally. Here's the data I found for both the angle and the distance judgments, and it leads to a pretty consistent picture of this compression in the in-depth dimension for any method and for both angle and distance data. I did a second experiment that was three-dimensional and allowed me to also be able to, it was done in an auditorium, so I was able to turn out the lights and get reduced Q judgments. But I'm going to just go on because it gave essentially the same results. Because I want to get to my more recent things before I end, and I know I only probably have about 5 minutes. A number of other studies, not just mine, have shown this, that the in-depth dimension of visual space is compressed compared to the frontal dimensions. This compression, also known as the anisotropy of visual space, makes in-depth oriented stimuli seem shorter than physically equal stimuli that are oriented frontally. But if you take all of that literature together, the conclusion you come to is that the degree of compression in the in-depth dimension of visual space, which is expressed by this compression parameter, I'm going too fast, but that this compression parameter then is the ratio of in-depth to frontals judgments for physically equivalent stimuli under the same conditions. And once again, if C is equal to 0.5, this indicates the same physical stimulus seems to be half as large when oriented in depth as compared to frontally. And I did a meta-analysis of the literature I could find that would give me data of this type. I couldn't find many things, although I'm sure I missed a lot. But what this literature showed to me is that the compression of the in-depth dimension of visual space is not constant, but it's a function of distance from the observer. So I performed a small meta-analysis using 59 cases derived from 10 studies as a function of the average distance from the observer to the stimulus under varying instructions and cue conditions. How am I doing on time?
You have 6 minutes.
Okay. And here's, yeah,
I have.
and here's a figure we've seen a couple of times, to my surprise.
Very
Just-
multiple figure.
Well, oh, thank you. In any case, here's the way you can read it. The filled symbols represent data collected under binocular conditions. The open symbols represent data collected under monocular conditions. And then the little X's down there are under reduced Q conditions. Diamonds represent objective instructions. Squares represent apparent size instructions. And looking at this figure, you can come to a few conclusions. One, if you just focus on the binocular viewing, what we find is that the compression of the in-depth dimension is large and nearly constant once you get farther out than about 7 meters, that it starts to flatten out at that point. But within arm's length, it grows, the compression is small, the compression parameter is large. And even when you get to the really nearest things, while closer than 1 meter from the person, we actually see kind of an expansion of the in-depth dimension compared to frontal. The second thing you see is that monocular judgments, where cues to depth are somewhat reduced, shows an even greater degree of compression. The compression parameter is even smaller. And then if you look at the reduced Q conditions, that produces markedly smaller compression parameters, leading to what I would say is a larger compression of visual space in the in-depth dimension. One thing I think is really interesting, personally, is that it doesn't seem that instructions matter. That when you look at it this way, both for the monocular and binocular conditions, it appears that essentially it doesn't matter whether you use objective or apparent instructions at all. We have something about visual space that's it's kind of invariant with the instructions that people use. I find that interesting. I did do an experiment to test this, because if you just kind of randomly select some data to do a meta-analysis on, particularly if you don't have a lot of data, then it's quite easy, you could quite easily come up with something that in some ways doesn't really reflect the way things really are, but might just be a selection bias. So I did an experiment with this guy named Gambino, where we tried to do this, test this directly in one single experiment. And so we had 39 observers, do judgments of tapes at tape lines at 7 different distances from the person, and then they used, this is the world I live in, they used the back of a tape measure to make their adjustments. I live in a cheap world.
No laser rangefinders.
No laser rangefinders, nothing like that. I'm using the back of tape measures. But in any case, neither here nor there. Instructions emphasized apparent size, because Baird and Bjornstorff already emphasized objective size. And what I found was just what you have seen many times. This, the top line is for frontally oriented stimuli. The bottom line is for in-depth oriented stimuli. We see underconstancy in both cases, but it's more apparent when you look at the in-depth oriented stimuli. The dashed lines, by the way, are the fit of the model to this data as well. In the model, the applied orientation tended to be less than vertical for frontal stimuli and greater than horizontal for flat stimuli. This implies that observers may not fully compensate for the orientation of the stimulus when making judgments. You can also calculate the compression parameter for each of the stimuli at these different distances, and what you see is almost exactly the same results we saw in the meta-analysis. Why does it work this way? Well, one thought is that what people really might be judging is the frontal, a comparison of the frontal versus the in-depth visual angles subtended by stimuli at different distances away. And if you look at that for observers of different heights, you find the same pattern in the data, but it's not as extreme. So I have a few speculations. People are accurate judging visual direction, so it might make sense they use the perceived size be based upon or be proportional to the visual angles of a stimulus. And that's what we found, but it's not as extreme as the predictions you would make based upon the visual angles alone. So this means people probably aren't fully taking account the orientation of the stimulus when judging size, because they can't ignore cues to physical size altogether. This brings us back to Brunswick, who talked about the regression to the real. We're probably seeing something of a regression to the real in the judgments. 1 minute? Okay, one last thing then. Gary. The affine model is still too simple. Gary Hatfield proposed a perspective-based theory for visual space similar to Galinsky, 1951. In this model, parallel lines converge to a vanishing point, and size shrinks as the distance from the observer increases. So we did a study on this. I hope you appreciate the picture, by the way, Gary. We did a study on this where we presented 5 squares in front of the person at different distances away. And the observers estimated the apparent size of the interior angles of those squares. And we did a second study that was just better. The perspective-based model, just as somebody had pointed out, Russell predicted, would say that the near angles in each square should seem smaller than the angles farther from the observer, whereas the affine model would not. And here are the results. The top line in each case, as you can see, within each square, angles nearest the observer were judged to be smaller than those farther from the observer in both experiments. That's the top line is the ones that are near to this, the angles that are near to the observer. The bottom line is the angles that are farther away within a square. And what's more, the distance to the square mattered. That as you got farther from the square, people made the angle smaller and smaller. Lastly, this does leave one kind of interesting puzzle that I present to Jim and Jan, and that is that the sum of the angles of the square, the sum of the angles should, in a Euclidean space, sum to 360 degrees, but in truth, it's only 360 degrees relatively near to the person, and then it goes down and down and down. I want to be careful in how I interpret that. I'm kind of interested in what you think, but maybe I've said enough then. So I'll stop there. I guess I had way too much in my presentation to be able to do in the time provided. Yeah.
So Mark, could you go back to your table summarising the results of the summarizing the results of the constancy studies.
Yeah.
It's one thing there that we had puzzled about in thinking about your.
I'll be there soon. It's one of the problems with putting these things up one at a time. There we go. Okay, here we are. We're almost there. Okay.
It's the one with the numbers from this study. So maybe it's slide before this one. This one. So I think the take-home message was that there's a general trend towards underconstancy. Here's what was bothering us. It seems like in the objective case we get the opposite trend. There's a trend towards overconstancy. But there's some hope that that can be explained away in terms of cognitive strategies. And that's we sort of have an error theory for why there's no trend towards underconstancy in those cases. What was bothering us is that in the table for apparent instructions, there what you seem to have is sort of constancy and a bit of a mix either way.
Yeah, I can. The reason I would give for that is that objective size is a pretty clear instruction, and projective size is a pretty clear instruction. But apparent size can be interpreted differently by different people who are doing the study. A person who, one person might interpret that as, I want you to tell me how big the stimulus is. And another person might be thinking, well, I want you to tell me something close to projective. And so it may well be, and this is just my speculation, that what we have here is kind of an averaging of strategies. And it may well, in part, depend upon how the researcher presents that instruction. I think if you really hammer home the idea that you don't think this is going to match physical size, then you probably will get something that really would be tending more towards underconstancy. And so that's why I have this kind of this overall sense that the more recent research is showing really more in the way of underconstancy, because I think some of the more recent research has really been really clear that you want people to talk about appearances as opposed to physical size. I could be wrong, but that would be my interpretation of it. Yeah.
Gary, is that a follow-up?
Do you know these
Sorry.
studies?
So I wondered, do you know the distances in these studies here, the 24 studies, I guess, of apparent instruction? Do you know the distances?
Not off the top of my head, I'm sorry to say.
I mean, so it was, for instance, Carl finding the more clear cases of underconstancy.
And he probably is using things that are further away than most of the
60
stuff
meters
that we're talking about.
away or something.
Yeah.
I could put a
Carl,
finger
you know
on
about
that.
Right.
Yeah. So one, I think you're absolutely right that there's no uniformity of these apparent size instructions. And so some studies found constancy, some underconstancy, and the ones that found underconstancy are, for example, studies by Hirsch Leibowitz, where he was very careful to tell his subjects that he's talking about appearances as opposed to the actual size. Also, Leibowitz, in finding underconstancy, used very large distances, so of like 60 meters, whereas some of these other studies by Carlson were indoors, just down at the end of the table. And so I think that the viewing distance has a really big effect.
Yeah, I agree with you. For instance, the study I did with Gambino, if you actually read the instructions we give, we really kind of make it very clear that we want them to talk about how it appears. And there we really did, of course, come up with underconstancy in both cases. So I think that might be part of the solution to the question. Anybody else?
Ying.
Kind of follow up. So here in this table, there is a clear difference between the parent and the objective instructions.
Right.
But in your meta-analysis did in 2016, there's no such big difference between these two types of instruction in terms of, at least in terms of this distance effect.
Right. Yeah, I mean, it's not the same thing. Because, I mean, there's two different figures we can kind of look at. You know, one is the Beard and Biersdorf data, where they used objective instructions. They had overconstancy for the objective instructions, underconstancy for the apparent instructions. But if you actually do the kind of the ratio, you end up with, you know, wait, excuse me, I'm wrong. If you look at Baird and Biersdorf, it's an orientation thing. And you can see that using objective instructions, they do get overconstancy for the frontal stimuli and underconstancy for the in-depth stimuli. But then if you take the ratio of in-depth to frontal, you'll get something that decreases with distance from the person. And if you look at our data where you know, we have these two things going down together with underconstancy, the frontal and the in-depth data, once again, you can kind of take that ratio and you end up with, you know, once again, something that fits along that curve that I showed. So that's what I mean by, you know, it's a different data. I mean, you do see different forms in the data. It's just that ratio that you get, you know, in some sense is invariant. Does that make sense?
Yes, yes, yeah. Okay.
Does it make, I mean, yeah, okay, yeah.
Is this a follow-up on these points, or I have you in the queue? I have you in the queue. So okay, Alex, did you want to follow up or to interrupt you?
I was wondering, the number 5, this is what they call, are these studies from 1930s? Or are these studies from 1980s, or what?
They're from a range of times that range.
5 ones.
Yeah, they range from the 1920s up to the 1980s. And so that's some of the early ones. All you can do is make a judgment about whether there's overconstancy or underconstancy. You have in effect a single data point. Whereas some of the later ones, you know, your judgment is based upon more than one data point, and you're comparing the far stimulus to the near one, you know, to make this judgment.
We cannot discount them just because people are learning their craft.
Yeah, well,
know what instructions to give.
I mean, this is my feeling. You know, I think that people like Thowless and Brunswick were really careful researchers. I think that there's no reason to throw out their data just because it's old. And so I kind of feel like that the ideal for us would be to be able to account for all the data that has come across time. You may be, it's possible you're right that they didn't, you know, that somehow we're getting better at our craft, but I'm willing to accept what they did as being good data.
Yeah, thank you. So thank you for that talk. So the way you, on your very first slide, define visual space is that it's the space as we consciously experience it.
That's what I'm hoping.
Yeah, but so, like some others, I mean, most people weren't as explicit as how they understand visual space, but some others here, I mean, I'm sort of talking to the psychologists in the room, seem to understand visual space as a space that is determined, the details are going to matter, but, you know, here's one gloss, by information processed on the basis of patterns of stimulation. Sure. And then we consciously experience some of that information, but some of that information may guide our actions without us consciously experiencing it. Right. And it seems the details here, what exactly is constitutive of visual space, really matters for a lot of the stuff that went on further. Yeah.
I agree with you. Yeah. That's why I put that stuff up there.
Right, right.
Because, you know, basically the difference between somebody like Gary, who I think has a more unitary view. Is that fair, Gary?
Unitary about?
About, you know, that there is a visual space. It's largely one thing.
Visual space.
Okay, well, there you go. In any case, some people who want a unitary vision, you know, are forced into this kind of odd situation where the data doesn't fit their impression. And the way you can manage to justify that is by saying that a lot of the data out there just doesn't reflect conscious experience.
Right. So if you're a unitary person, then it's a very good idea to have information processed on the basis of patterns of simulation notion of
Right.
visual space, where some of that might be conscious and others not. Whereas, yeah, I get
And
that,
so,
yeah.
you know, then you're brought up to a second question. How do you know the difference? You know, how do you know which of them are reflecting conscious experience and which of them don't? Now, the easy way to do it is my way of doing it, which is not making a call. Just saying that really what we're depending upon is the data that we have, and that we define visual space in terms of the data, and then feel that people are trying to reflect something about conscious experience when they make those judgments. On the other hand, I think Carl is making a pretty good argument that perhaps some things are some of the data that we're getting are reflective of conscious experience, and some of it's not. And so what you would need in order to shake me off of my kind of feeling that there are multiple versions of visual space is that you need somebody like Carl knocking down one after another until only one is left standing. And until that happens, I'm a multiple visual space guy.
I mean, of course, you can be a multiple visual space guy and nonetheless understand visual space.
It's maybe not being conscious.
Yeah. So I think those two things kind of are orthogonal.
And you know, you're absolutely right. I think that we hope that the judgments that people make somehow reflect their experience. Otherwise, it might not be very interesting to do the research, because if it's just number generation as a function of instructions, that's not as interesting as if it tells us something about experience.
Sure.
You know what I mean?
Yeah, absolutely.
Yeah.
A quick follow-up for you?
Yeah, if visual space is defined as visual, as how we experience visual space, then shouldn't one datum there is that visual space is unified because that's the way we experience it? There's just one.
But do we? That's the question. Is it possible to have more than one coherent experience of visual space? Here's something I'll say that I think that a lot of people might disagree with, but if you were to think of visual space as defining the coordinates of what's out there, that when I look into this room, I see that one person is closer to me than another, and I see that one person is to my left and another is to my right. But that doesn't say what the metric is that we are placing upon those coordinates. So it is conceivable that we are viewing more than one space as stimulus conditions change, the actual space that we perceive might change, as our attitude towards what we mean by size and distance changes, then it's possible that our space that we perceive could change as we take a different task where we ask people to do clever things about putting things along a line. That could actually change the experience we have of the space. I'm not saying it does, but it's possible that you could have, if you will, one picture in your head, but multiple spaces, because of the way that we deal with our metric relations. Does that make sense?
Yeah.
I just asked. Yeah.
Sorry.
It's just a straightforward. So this is a real novice question, but how are you counting or individuating spaces? So you kind of went back and forward between saying there isn't a single geometry and saying there isn't a single space. Is the idea that there's that for something to count as a space, there's got to be a single geometry which captures all of them? Mm-hmm. So you couldn't have variations in geometry within a space or something like that. Mm-hmm. Okay.
I think you could.
That's what I was wondering. Yeah. So then the two ideas come apart.
Right.
So, what I'm trying to track the discussion here, and I'm sort of I'm kind of confused at the first level, which is how we counting spaces.
I think that you count spaces by the data they produce, And if they produce different metric relations, for example, I would think of that as a different space. And so, for example, if you were to go, for instance, to the direct estimation data, one would say that because your judgments are different in reduced Q conditions as they are in full Q conditions, that, in my mind, is reflective of a different kind of visual geometry.
Okay, so I mean, really just the thought is if people are going to argue and debate these issues, the obvious thought is they better have the same criteria for counting spaces in mind, otherwise you're going to get a lot of confusion.
I think anytime you do research in this area, you have to be very explicit about what your conditions are, what your instructions are, because if my way of looking at it is correct, you're going to get a different space depending upon that combination. And so therefore, you really have to lay that out when you talk about it.
I mean, maybe one way to put it is that the thesis that you might refute with this data is to say that for example, that the correct geometry for describing visual space under all circumstances might be Euclidean. And you say, well, no, that can't be.
And that doesn't work.
That's right. And so the idea of there being different spaces is that you might need different geometries for any given task to make sense of the data.
The goal is to be able to basically, if I could be the geometry god, what I would want is this wonderful equation that would say, here's my size, distance, and angle judgments as a function of all this stuff. And I'd have like one equation that would put these factors into it. And then you would have like that would be God's equation for visual space. I'm not God, so I don't have that equation. But that would be the goal, I think.
Did you look at, I like the business where you compare the visual angle of the flat to the parallel, but did you look at any other optical variables like how disparity between the endpoints changes as you vary distance or declination angle with the horizon ratio?
That would be a very good thing to do, but no, I didn't. I was just casting for kind of like what I thought was probably the most relevant variable. And when I did this analysis of how, in physically, the ratio of how the visual angle changes as a function of distance for both in-depth and frontally oriented stimuli, I saw that the pattern was very much the same. It was striking, but not as extreme. So that's why I kind of use that as my theory, but I'm quite happy to think that there are other ways of looking at it that might be superior. But that's basically, I guess the answer is I didn't think about it. and I maybe it would be great to think about it.
And if I could ask another question. So you, at the very end, I know you had to rush by quickly when you talked about that angle.
I shouldn't have spent as much time in the early stuff, frankly. But
I'm curious how you did that. So did the subjects estimate what the angles were, or did they?
Yeah. Okay.
Or did they set the angles and then you measured them?
Prophet. He had this wedge that he used, an adjustable wedge, that basically allowed people to adjust the size of an angle, and then you can read off. Then we had it set up so we could read off the back what the angle was.
So this is not a subjective angle.
So it's subjective in the sense that it's the person is trying to match the angle to what's out there, and that they may not adjust it to be the same size as the angle physically is. And in fact, they don't. As you get further from the person, those angles tend to vary more from what would be theoretically true or what would be physically true. Does that make sense?
I'm wondering, in some of your other experiments where you actually have them make subjective. So they're doing a comparison and you're measuring the physical angle that they set.
Yes, right.
All right. But in some of your other experiments, they subjectively judged what the angle was.
Right.
And they're two very different procedures.
Absolutely. But I will say this about that, and that is when I did that research, in those two studies I went past very quickly. We use multiple methods for them to be able to make the angle judgments. In fact, 4 different methods, although mapping in some sense gets counted twice in this. They did maps, they did category estimation, they did magnitude estimation, both numerical methods like you're talking about, but I also for angles had them match the angle to an angle on a card, which is similar to the thing that we did with profit wedge, but in this case I gave them a series of angles that they could match to the to what the angle was out in the field. So they actually use both types of methods, both numerical estimation and a perceptual matching type of task. And the thing that's interesting is that that didn't make it as much difference as you would think. They both showed this close to the same degree of compression of visual space in the in-depth dimension. That make sense?
Yeah.
Yeah, I mean, it's not quite, I mean, if we look at the data more closely, we might be able to make a distinction. I think the perceptual matching was a greater degree of compression compared to the numerical estimates. But I have to look at that.
I guess the only point I would make is that if you're subject to doing a match and then you're measuring what the physical max is, you're sort of mixing intrinsic geometry with extrinsic geometry, and a better procedure, you know, angle magnitude estimations are probably not the cleanest thing in the world to measure. But if you had some way to keep it intrinsic, I think that would make that result a bit more interpretable.
I hear you, and no doubt you're right. What would you say about that, the case where we use the wedge-like profit in order to judge angles? Would you consider that intrinsic?
I have to think about it because, as again, you're mixing these two different conceptions.
Yeah.
And you can easily turn yourself in knots when you do that.
I hear you. I mean, in my heart of hearts, I think I'm extrinsic. You know, I think I'm comparing what's physical angles to perceptual measure that I get from making those adjustments or from having them generate numbers. But, you know, you're probably better at making that judgment than I am, I think.
I've got 2 more people in the queue. So really quick follow-up though, Robert, if you want here, but then I'm going to try and squeeze.
Yeah, so this is just a really quick question, but in addition to using stakes in the ground, if people use textured geometrical forms, a big white triangle covered with polka dots or something on the ground.
Yeah.
I mean, just 3 stakes in the ground, that's not a lot of information to go on.
You're right. And that is a problem, although it's kind of similar to some of the things that we've heard earlier.
Right.
Part of the reason why I thought that was the way to do it is that you wouldn't then be making 100% call about the straightness of a line. And then, you know, you would allow, if it were non-Euclidean, and I'm not sure my method is getting at this, but if it were, you know, you wouldn't have that constraint. The other thing is that it allowed me to make a tremendous number of judgments. Because if you pound 10 stakes in a field and use pairwise every combination, you can get a lot of judgments that vary across orientations and distance from the observer and all these other factors very quickly. And so that was another reason why.
Bill?
So just going back to the multiple visual space, multiple geometry question. So what if there just is no visual space? Right, so we kind of impose this construct on our experience. And what if every time I'm making a judgment about something or I'm doing a task, I'm just using a different piece of information?
Sure.
Right? And some of that information, may be exaggerated or underestimated or overestimated, but there's no reason that it would all hang together. Right? So if I'm making a distance judgment, right, I might have really great constancy because I'm using a variable that maybe egocentric distance. would lead to that. Or if I'm doing size judgments, I'm going to use a different variable that might lead me to get underconcentrated in some cases. And so there's no reason to think of it as a coherent.
Yeah, actually, I think that we're pretty much on the same page in a way. Because earlier we were kind of talking about this issue of how could you have, one sort of, I know I'm getting in trouble by saying this, how can you have one picture in the head and have multiple geometries? And the answer is pretty much exactly what you're saying, that, if you use a different method, if you use a different attitude, you may get a perfectly consistent geometry for all the judgments you make of that type, but you might be picking up on something different when you go from one measure to another, leading to what I would think of as a different geometry for the space. So yes.
So that's what the idea that there's a consistent geometry is really more a matter of our description of our data than it is perhaps what's driving.
Yeah, I mean, I was talking to somebody about how basically I kind of feel like we need to back off a little bit on how much is found in the image in the head and how much, might be a function of, instructions and attitudes and things like that might be layered on top of that. And so what you're saying is, I think very consistent with that what's provided by the visual system may be something that we can deal with in a very malleable way.
Organizers, I have one more question, but it is time up.
Let's have the last one.
Last question. EJ, you get the last question.
Oh, man.
Good.
I was just kind of wondering has anyone looked at the effect of attention on the compression parameter? Because that's sort of a natural place to look if you're, to use your image metaphor, one idea would be that, there's not a single image. Attention warps the image.
Yeah, that sounds great. I don't know of any work of that type, but I have sometimes conceived of the possibility that the shape might be warped by the presence of objects, that it might be different in the foveal area than it is if you include things outside of that, in attention outside of that. Those are all things that I don't know of any data on, but I think they'd be really good things for people to look at. And in my way of looking at things, you could well get, those things changing the kind of the relations in very interesting ways. In fact, there actually, I want to be careful, there are some data where people have looked at the presence of frames on the judgments that people give, and it does make a difference. And so
you have data yourself.
I do. Tell me.
Your instructions in telling them what they should attend to in terms of what the information is.
Well, that's a good point.
Angle.
That's a good point.
The objective size.
I didn't even know it.
This morning, there's kind of fixation, right? You can say this target compared to the other, we get one result, fix the other target compared to that, we get a different result.
But I guess my thought was that we don't need to be thinking that there's one fixed experience, then.
Right.
It could be that attention is actually changing the experience.
I think that's a good hypothesis. And as all good hypotheses, it deserves to be either falsified or confirmed.
Alex, you're one of the organizers. You want to follow up, or you want to? It's your prerogative.
There was a poster at VSS conference, Vision Sciences Society, a few years ago, and it won some award.
Wow.
And I can dig it out if people are really interested.
Sure.
On the post, what caught my attention was somebody had this method for making some kind of judgments about relationships among points that are in a small neighborhood. Mm-hmm. And then he would put an image of a rabbit or a horse or a house or something next to it. So you're judging local neighborhood spatial relationships that are always the same, but next to it there is some rabbit or a horse or something. And then the poster presented these data in some kind of visual way, and they look very much like if you have let's say a bed with some texture cover on the bed, and then you put a physically heavy object, and it literally, the surface bends down, and then it creates these almost like gravitational fields around it. And so that is following on this. That space may be distorted by the presence of objects, and I can easily imagine moving attention away is kind of a zooming lens kind of.
Why isn't the Muller bioevolution an example with the flanks and size change?
Yeah, that would be. But somehow it is attached to the flankers. The other, anyway, but
There's,
there are data.
there's so much to do.
Yeah.
So we're too old to do it all.
I'm too old to do it all.
So let's thank Mark again.